we discover an asteroid. We have a couple of data points on its position in the sky. You look at its speed, you get a Doppler shift on it, you get its...
The probability of an Earth collision between 2175 and 2196 has been revised to 0.037%, corresponding to a score of minus 1.71 on the Pu scale. If such an impact were to occur, it is expected to release about 1,200 megatons of energy, which is significantly more than the largest nuclear bomb ever tested, the Tsar Bomba, which yielded 54 megatons. The Tunguska event, known as one of the most powerful asteroid impacts in history, was estimated to release between 3 to 5 megatons, with some studies suggesting figures as high as 20 to 30 megatons. Bennu is not the only asteroid being monitored by NASA. Another significant object of interest is Apophis, which was first spotted on June 19, 2004, by Roy Tucker, David Tholen, and Fabrizio Bernardi at the Kitt Peak National Observatory. Later that year, on December 21st, Apophis passed about 9 million miles from Earth. Earlier observations from March of the same year were identified in December, helping scientists refine their calculations of its orbit. By January 2013, radar observations confirmed that the chances of Apophis impacting Earth in 2036 were less than 1 in a million. By February of that same year, the probability was reduced further to just 7 in 1 billion. In 2036, Apophis is expected to pass close to Earth twice, once in March and again in December, at a distance roughly one-third the way to the Sun, similar to how Venus approaches Earth every 1.6 years. Simulations in 2013 suggested that the Yarkovsky effect could push Apophis through a keyhole in 2029, potentially bringing it closer to Earth by 2051. However, the odds of this occurring were estimated at only 2 in 1 million. Later radar data collected in March 2012 provided more precise measurements of Apophis's trajectory, and that same month, scientists announced that it had no chance of colliding with Earth for at least the next 100 years. By 2021, uncertainty surrounding Apophis's closest approach in 2029 significantly decreased, improving future predictions. At that time, 6 other asteroids had higher cumulative scores on the Polaro Technical Impact Hazard Scale than Apophis, though none had a Torino scale rating above 0. Still, Apophis is expected to remain a potential hazard for thousands of years unless it passes close enough to Venus or Mars to alter its trajectory. The discovery of Apophis in 2004 was surprising, as scientists estimated that asteroids of this size or larger coming close to Earth happens only about once every 800 years, with collisions expected only once in roughly 880,000 years. NASA continuously tracks near-Earth objects. For instance, an asteroid called 2024XU9, about 110 feet wide, similar to an airplane, is expected to approach Earth on December 14, 2024. Following that, another asteroid, 2024XB16, approximately 47 feet wide, about the size of a house, will come close on December 15, 2024. On the same day, another asteroid named 2024XF4, about 200 feet wide, similar to an airplane, will also pass nearby. On December 16, 2024, 2 more asteroids, 2024XY5, 71 feet wide, and 2024XB6, 56 feet wide, both comparable to a house, will come close to Earth. Earlier, on October 18th of the same year, a larger asteroid, 2024 RV50, estimated to be about 710 feet wide and comparable in size to a stadium, will also pass nearby. NASA's Jet Propulsion Laboratory consistently monitors these near-Earth objects to assess the risks of collision, and while these objects are closely watched, the likelihood of a serious impact remains low due to the vast distances involved. However, asteroids aren't the only concerns in space. Another significant potential threat comes from the sun's solar flares, which are massive bursts of energy released by the sun, can occasionally cause serious issues. When a powerful solar flare occurs, it sends strong radiation and charged particles into space, which can disturb Earth's magnetic field and trigger geomagnetic storms. These storms can disrupt radio communications, affecting GPS systems and air traffic control, and intense radiation from solar flares can damage satellites, potentially leading to communication outages. Power grids on Earth are also at risk, as solar flares can create strong electric currents that might result in blackouts and large-scale power failures. Despite these threats, solar flares can create stunning auroras, known as the Northern Lights, when the sun's charged particles interact with Earth's atmosphere. While Earth's magnetic field provides some protection, severe solar storms can still have widespread effects, making forecasting space weather increasingly important to mitigate risks. However, the sun isn't the only potential threat, and the chances of a rogue star colliding with Earth are extremely small, primarily due to the vast distances between stars in the galaxy. For instance, the rogue star HIP 85605 is expected to pass relatively close to our solar system at a distance of about 8,000 astronomical units, or 0.04 parsecs, in roughly 240,000 years, which is considered a near miss in astronomical terms. Similarly, GLE 710 is predicted to pass through the Oort cloud, the farthest region of our solar system, in approximately 1,290,000 years. While this event may disturb the Oort cloud and send many comets toward Earth, the likelihood of a rogue star directly colliding with our planet remains very low. Another significant threat that most people may not be aware of is gamma-ray bursts, GRBs, recognized as the most powerful and brightest electromagnetic events in the universe. These bursts are brief yet extremely intense flashes of gamma rays, the highest energy type of light, lasting from just a few milliseconds to several minutes. In that short time, they can emit more energy than the sun will produce over its entire lifespan of 10 billion years. The discovery of GRBs dates back to the late 1960s, when the United States launched satellites called Vela to monitor compliance with the Nuclear Test Ban Treaty by detecting gamma rays from nuclear explosions. In 1967, these satellites detected bursts of gamma rays that appeared unrelated to nuclear activities, leading to the confirmation that these signals originated from outer space. The first official research paper on GRBs was published in 1973 by scientists R. H. Kell, Ian Strong, and Roy Olin at Los Alamos National Laboratory. GRBs are typically categorized into two main types based on duration: short-duration GRBs, lasting less than 2 seconds, thought to occur when two neutron stars merge or when a neutron star merges with a black hole, and long-duration GRBs, lasting longer than 2 seconds, believed to result from the collapse of massive stars during supernova explosions. If a substantial amount of gamma rays from a GRB were directed towards Earth, the consequences would be devastating. The intense radiation could strip away the ozone layer, which protects life on our planet from harmful ultraviolet radiation. Without this protective layer, the surface would face lethal levels of UV radiation, leading to widespread ecosystem damage and a sharp increase in skin cancers and other health issues. Additionally, the gamma rays would ionize the upper atmosphere, generating nitrogen oxides that could cause severe atmospheric changes, potentially resulting in a gamma-ray burst winter, which could lead to drastic climate shifts, global cooling, and disruptions in agriculture and food supplies. The intense radiation could also directly damage DNA and other biological molecules, causing mutations and potentially leading to mass extinctions. Transitioning to another significant cosmic event, black holes are some of the universe's most fascinating yet mysterious objects, characterized by regions in space where gravity is so strong that nothing, not even light, can escape. Black holes form from the gravitational collapse of massive stars at the end of their life cycles. The concept was initially proposed by John Michel in 1783 and later by Pierre-Simon Laplace in 1796, but it wasn't until the 20th century that the idea gained traction, thanks in part to Albert Einstein's theory of general relativity. The first physical evidence of a black hole came in 1975 when Cygnus X1, a strong X-ray source, was identified as such. In popular media, black holes are often depicted as cosmic vacuum cleaners, voraciously sucking in everything around them, while films like Interstellar and Event Horizon have portrayed them as gateways to other dimensions or alternate universes. Although these portrayals are exciting, they are not entirely accurate, as black holes do not actively pull objects in but instead exert a gravitational pull like any other massive object. If our solar system were to encounter a stellar mass black hole, typically around 10 times the mass of our Sun, it could cause significant gravitational disturbances, altering the orbits of planets or leading to potential collisions. The intense gravitational forces would generate tidal effects that could stretch and compress objects, resulting in massive geological activity on Earth such as earthquakes and volcanic eruptions. As the black hole gets closer, it would begin to accrete matter from the solar system, creating an accretion disk that emits high-energy radiation, which could strip away Earth's atmosphere and sterilize the planet's surface. In the case of a supermassive black hole, which can be millions to billions of times the mass of the Sun, the consequences would be even more catastrophic. Its immense gravitational pull could disrupt the entire solar system, potentially tearing it apart, while the radiation from the accretion disk could make Earth uninhabitable long before the black hole itself reached our planet. Adding to the concern, some black holes can also become rogue, known as free-floating, nomadic, or orphan black holes, which are interstellar or intergalactic black holes, rogue black holes, which typically result from collisions between two galaxies or the disruption of merging black holes, are estimated to number around 12 supermassive black holes at the edge of the Milky Way galaxy. In January 2022, astronomers reported the first clear detection and mass measurement of an isolated stellar black hole using the Hubble Space Telescope alongside microlensing observations from the MOA, microlensing observations in astrophysics, and the OGLE, optical gravitational lensing experiment. This particular black hole is located 5,000 light-years away, has a mass 7 times that of the Sun, and moves at approximately 45 kilometers per second. Although other rogue black hole candidates have been detected indirectly, the potential threat they pose to Earth, the solar system, and the Milky Way is significant. If a rogue black hole were to come close to our solar system, its immense gravitational pull could disrupt the orbits of planets, potentially ejecting them into interstellar space or causing collisions. The gravitational forces from the black hole would generate intense tidal forces, stretching and compressing objects, which could lead to catastrophic geological activity on Earth, including massive earthquakes and volcanic eruptions. As the rogue black hole approaches, it would begin accreting matter from the solar system, forming an accretion disk that emits high-energy radiation capable of stripping away Earth's atmosphere and sterilizing the planet's surface. A collision with a rogue black hole could ultimately result in the total destruction of the solar system as planets, moons, and other celestial bodies are torn apart and consumed by the black hole's event horizon. The Milky Way might also be affected if the trajectory of the rogue black hole intersects with the galactic core, potentially disrupting the orbits of stars and other black holes, and leading to a cascade of gravitational interactions that could alter the galaxy's structure. However, the likelihood of a rogue black hole colliding with our solar system or Earth remains extremely low due to the vast distances between objects in space. For example, astronomers have identified a potential rogue black hole about 5,200 light-years away, moving faster than nearly all visible stars in its vicinity, but the probability of this or any rogue black hole getting close enough to cause significant disruption is minimal. The vastness of space and the relatively small size of black holes compared to the distances between stars make such collisions exceedingly rare. NASA has also been closely monitoring comets, another space phenomenon that, while not posing as much risk as others, still warrants attention. A comet is a small icy body within the solar system that heats up and releases gases when it comes close to the Sun, a process known as outgassing. This produces a gravitationally unbound atmosphere called a coma around the comet's nucleus, sometimes accompanied by a tail of gas and dust. Such phenomena occur due to solar radiation and the outflowing solar wind plasma acting upon the comet's nucleus. Comet nuclei vary in size from a few hundred meters to tens of kilometers and consist of loose collections of ice, dust, and small rocky particles. The coma can extend up to 15 times the diameter of Earth, while the tail may stretch beyond 1 astronomical unit. If a comet is bright enough and sufficiently close, it can be viewed from Earth without a telescope, often subtending an arc up to 30 degrees, which is 60 times the apparent size of the Moon in the sky. Comets have been recorded since ancient times by various cultures and religions, with many comets and asteroids believed to have collided with Earth during its early history. Some scientists assert that comets bombarding the young Earth around 4 billion years ago may have delivered significant quantities of water that now fill the oceans. Others have raised questions about this theory, noting the detection of organic molecules, such as polycyclic aromatic hydrocarbons, in comets, which has spurred speculation that comets or meteorites may have brought life's precursors, or even life itself, to Earth. In 2013, it was proposed that impacts between rocky and icy surfaces, such as those on comets, could create amino acids through shock synthesis, allowing smaller molecules to condense into larger macromolecules that might serve as life's foundation. In 2015, scientists discovered substantial amounts of molecular oxygen in the outgassing of Comet 67P, indicating that such occurrences may be more common than previously thought, thus being less of a clear indicator of extraterrestrial life. It is suspected that comet impacts over long timescales have delivered significant quantities of water to Earth's moon, some of which may have survived as lunar ice. Comet and meteoroid impacts are thought to be responsible for features on the moon's surface. As of November 2021, more than 4,000 known comets had been identified, but this represents only a small fraction of the total potential comet population, estimated at around 1 trillion in the outer solar system. On average, approximately one comet becomes visible to the naked eye each year. However, many of these are faint, and such a threat cannot be dismissed, as comets follow more random paths compared to asteroids, making them harder to predict and potentially dangerous. Additionally, another significant event, known for its brilliance, could lead to a mass extinction if it were to occur close enough to Earth. Supernovae are among the most powerful and luminous occurrences in the universe, marking the explosive death of a star. They happen when a star exhausts its nuclear fuel and undergoes a catastrophic collapse, resulting in a massive explosion that can outshine entire galaxies for a brief duration. There are two main types of supernovae. Type 1 occurs in binary star systems where a white dwarf star accumulates matter from its companion star until reaching a critical mass and subsequently explodes. Type 2 takes place when a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel and experiences core collapse under gravity, causing a violent explosion. The discovery of supernovae dates back to ancient history, with the earliest recorded observation occurring in 185 AD by Chinese astronomers, but it wasn't until the 20th century that scientists began to understand the true nature of these cosmic events. In 1934, Walter Baade and Fritz Zwicky at the California Institute of Technology coined the term supernova, proposing that these explosions stem from the collapse of massive stars. The first modern supernova to be extensively studied was SN 1987A, which took place in the Large Magellanic Cloud, a nearby galaxy. This event provided valuable insights into the mechanisms underlying supernova explosions and their significance in the universe. If a supernova were to explode in close proximity to Earth, the consequences could be catastrophic. The intense radiation and energetic particles emitted from the explosion would pose a significant threat to life on our planet. Gamma rays and X-rays from the supernova would strip away the ozone layer, which acts as a shield against harmful ultraviolet radiation. Without this protective layer, the planet's surface would be exposed to lethal levels of UV radiation, leading to widespread destruction of ecosystems and a dramatic increase in skin cancers and other health issues for living organisms. Moreover, the supernova's shockwave would have a profound impact on the solar system. The intense energy burst could disrupt the orbits of planets and other celestial bodies, potentially causing collisions and altering the solar system's stability. The shockwave would also compress and heat the interstellar medium, possibly triggering the formation of new stars and planetary systems. See you in next video.